Yes.
Okay, should I? And now.
Let me say a few words, perhaps. Yeah, I think we can get started. Today is our great pleasure to welcome Dr. Yunan Yang to give a talk today. And Yunan received her PhD in mathematics in UT Austin, under supervision of Professor Björn Almqvist. She's now a Quran instructor. Her dissertation was very interdisciplinary. It's research between numerical analysis and the geophysics. Many focus on analyzing and applying optimal transport and the inverse problem. Yunan was honored as one of the 32 Risen Star in the competition in data science by the Oden Institute at UT Austin. She also received the first place in the 19th IMA Leslie Fox Prize in numerical analysis. She's actually on the job market, but she got, Yunan, can I say it? Perhaps maybe not. But she will join some good university soon. Anyway, Yunan, it's all yours, please.
Thank you very much for the introduction. I'm so sorry, everybody, that there's some technical issue. I think I'm not very familiar with WebEx, and it's totally my fault. So today is my great pleasure to be able to present some of my work. And I realized the seminar's title is Mathematics in Imaging, Data and Optimization, and I feel I perfectly fit into this category. So today I want to talk about using optimal transport-based techniques for inverse problems and also explain the particular properties, which is implicit regularization when you make such a choice. I work on computational optimal transport and computational inverse problems. So this topic is in the intersection of these two. So first of all, I want to give a quick introduction of what type of what is the inverse problem, which may be very familiar to some of you. So inverse problem is a counterpart of forward problem. So in forward problem, which like what we refer to as modeling or simulation step, is usually the setting that if you give me the physical parameters, I want to mimic the physical process as vivid as possible. So this process is given the parameter and we want to produce the data, and the data sometimes is regarded as a solution to ordinary differential equations or partial differential equations. So numerical solution to PDE particularly focus on this process. While in most of the applications in real world, it's very common that it's exactly the physical parameter that we don't know a priori, such as where is the source of the sound or the source of the heat, and also a boundary condition or initial condition. We don't know a priori. And we want to infer those important parameters from the data that we can see. So the data sometimes, if we are lucky, can be exactly the solution to partial differential equations. But if we are not super lucky, it can be part of those solution or some functionals of the solution. But they are the only information available for us to infer what's going on and what's the parameter. And a very common inverse problem involve how to detect the source of an earthquake. And recently, 2 years ago, we were able to produce a black hole image that was in the news. So that also was a standard inverse problem. And also common medical imaging such as X-ray and CT all belong to the category, given the data and try to infer what is the parameter.
Sorry for interruption. So I was wondering if you move the slides. Seems like we can just see the first slides.
I see. I think that's because.
Can you see? Yeah.
Okay, maybe it's better in this way. Okay, sorry. So yeah, I have moved the slide. It could be when I was having the full screen, it cannot show. Okay.
Now I can see it. Thanks.
Yeah. So this was the forward problem, and then this is the inverse problem that we are interested in. So the particular inverse problem that I will talk about is about Sesame Inversion, which is one type of inverse problem corresponding to wave propagation. So this is in the same category as X-ray, CAT scan, and ultrasound. Instead of doing wave propagation to part of our body tissue, like those medical imaging, Sesame Inversion do the wave propagation to part of the Earth, So the scale is very different. And also the setup is very different, which I will describe as the following. So it is a wave propagation problem. So we have a source, and this source is an artificial source we created, like geophysics they created. It can be a vibrate track, and this track bounce back and forth at a certain frequency. So it generates some signal like a source. And if the energy is large enough, that signal will propagate through the subsurface, and some of the signal will come back to the surface where we can observe. So those type of waves that come back to our surface involve continuous refraction, that continue refracted and finally go back to the surface, or direct reflection. Like there's a discontinuity, and when the wave meet a discontinuity, there will be reflected back to the surface. And once the wave go back to our surface, they are captured by the orange sensor, orange dots here, which represent the sensors. So the sensors are placed at different locations, and each sensor continuously sample the time data. So in the end, each sensor will sample a time series of the data, which we usually call a trace. And in the end, our data will look like a lot of those traces placed together. So each of these Vigo that you see on the left figure can be considered as the data from one of the sensor. And so the Vigo is in time domain. And the positive part means the amplitude is positive. So the black part means the amplitude is positive. And the black part means the amplitude is negative. So that's a waveform. And once we place all of the orange dots, the signal received from those orange dots together, we get this continuous waveform. And the reason it's continuous is because what this orange dot observe is highly correlated with what its neighbor orange dot will observe because of the wave property. So that's the data available to us, which is both time domain and the spatial domain information. And we want to use this amount of information to inspect what's going on underneath the ground, which can be, for example, the density or wave speed. Because different material, let's say sand or oil or water, they have different density and also have different velocity. So that number, that velocity, for example, is one important quantity for geophysics to identify what is the material. So that has geology meanings. So one particular benchmark that's in this community and also in a lot of my presentation today is this so-called Mammoothy model. It was created in the 1980s to mimic the complex geology under the Gulf of Mexico. So this is so the variable was the inverse. The parameter we want to reconstruct is a function of space. So that's the target. So this is the physical application, and as a mathematician, we can put everything back to the mathematical framework. So the forward problem in this setup, I put into acoustic wave equation. But I want to mention that it's not just limited to acoustic wave equation. In realistic setting, the wave equation or the forward model can be elastic wave equation, or even more complicated viscoelastic wave equation with damping parameters in it. So I just use acoustic wave equation here, for example, but in really seismic community, they study all kinds of wave model as a forward model. So consider this is our forward problem. So the forward problem is, if you give me the source, tell me the initial condition and the boundary condition. Then if you tell me what is the variable coefficient, I will be able to solve this wave equation numerically or analytically and obtain the solution U everywhere on the domain. And that's something over the decades we have been knowing how to do pretty well. So this map that from M to U is our forward map. And in this inverse problem, it's a half space problem, as you can see earlier in that setup. We cannot observe the boundary management everywhere as, let's say, a medical imaging. When we do a CT scan, actually the CT machine can observe the wave 360 degrees. But that's not the case for Sesame Inversion, because you can only have the measurement in the upper surface. So there's a limited boundary data out there. And the inverse problem is using that amount of limited solution on the upper surface boundary. We want to use them to reconstruct the parameter M, and that's the inverse problem we are facing. One comment I want to make is, although we learned this wave equation as the first type of equation in PDE course, we learn it as a very standard second order linear equation. but the linearity is really with respect to the right-hand side. So basically saying the connection from S to U is linear. That's without any doubt. However, in this case, it is M that I want to reconstruct, and that increases the difficulty of the problem dramatically. So unfortunately, the map from M to U and together with the map from U and M are highly nonlinear. And that's a big difficulty with this problem. And this is, on one hand, mathematically, we have a nonlinear map that we don't know the explicit solution. But on the other hand, this problem has a huge application to extract hydrocarbon and many others. So geophysicists or practitioners reformulate the problem a little bit. Instead of saying, let's figure out what G looks like, we formulate it as a PDE constraint optimization. So instead of looking at what G should be, we consider the parameter we want to find M as the particular one that minimizes the difference between what we can observe from the orange dots versus what we can compute synthetic data based on my current guess. So I can keep making my prediction, keep making my guesses. As long as I find a particular prediction that can minimize the difference between the synthetic data, which I generate from computers, versus the real data that I measure from the field out there, then I will consider that parameter is my true inversion reconstruction. So in this way, we no longer have to deal with G, and we just need to solve the forward problem, which is solving the wave equation again and again. Because given a particular guess, I need to solve a wave equation to obtain what that synthetic data is. So the problem now becomes a standard optimization problem. So we have an initial guess, we do a forward wave equation propagation, and we compare this true data and the synthetic data, and consequently, we have an objective function. And using gradient descent or other similar optimization algorithms, we update the velocity guess M and do it over again. So this is something we have been talking about in all kinds of optimization framework, but there's two particular things I want to bring up. One is the parameter M is not like a small size, because M originally is a function. Once we discretize, M can easily have 1 million variables in it. Therefore, our unknown is really large size, and that limit us only can do gradient-based optimization algorithms, such as gradient descent or BFGS. We cannot afford to do global optimization. So that's one situation, one limitation. Another is, although nowadays we know very well how to solve an acoustic wave equation, but the question is, the scale is very large in this situation. The domain that I need to solve the wave equation is in kilometers, that kind of scale. Therefore, solving wave equation is now still something that I can do in a blink of time. So I want to limit the amount of time that I need to solve the forward problem, so to simulate the wave. And these two limitations make the objective function very important, because under a gradient descent based algorithm, how the optimization perform is highly correlated with the convexity or some other properties of the objective function. And that's why in our research, we focus on the particular objective function and which one is better, and how a change of objective function will make things much better. So that's the motivation of the research. And the tradition.
Sorry, may I clarify something? So
sure.
Just the dimension of M. So basically, so if my understanding is correct, M is like a vertical slice of the Earth, right? It's not a on the surface. It's just a 1D signal. It's not a 2D signal. Is that right?
M is the one that underneath the ground. So
but yeah, that one's 2D. But your wave is a 1D, right?
If you only have one receiver, that's 1D. But we have so many receivers, so many outer dots. So our wave solution will also be 2D if your wave equation is 2D.
I see.
Yeah. Okay. So if your velocity in realistic case is 3D, then your observation will also be 3D correspondingly.
That's what I mean. That's what I mean.
Yeah.
Okay. So Yunan, can I also ask a question?
Sure.
So your gamma, I guess, corresponding to the data you measure at those orange dots. So they, yes. Only they are discrete in both your analysis and your algorithm.
They are not really discrete. Yeah. So I think Yeah, I think in realistic exciting is discrete, but usually in synthetic data, I make it a little more denser maybe than the realistic situation. And what we do is the objective function is the summation over the receiver. So I think that reflects the fact that it can be discrete. So the L2 norm is the signal's time domain L2 norm. So that's only in 1D. And we sum over all the receivers. That's actually,
okay.
Yeah. The
Thank you.
And in my synthetic situation, the receiver are much more than what people have in realistic setting. So this is a traditional objective function we integrate in time, in L2 in time, but also similar to like a summation of the receivers. Usually we will add some regularization to deal with some noise, etc. But even if we have regularization, there's two fundamental challenges that cannot be easily resolved just by adding a regularization. So one of the challenges is this is a highly non-convex optimization landscape associated with this objective function. The reason we can also see it easily. Earlier, we mentioned that the relationship from M to F, M is a parameter, F is the data. The relationship, because the wave equation, so the relationship is highly non-convex, it's highly nonlinear. And once we put the highly nonlinear function into this quadratic formulation, it doesn't turn out to be quadratic or even something related to convex. In the end, it is highly, highly non-convex. And another challenge, which is very common in all kind of L2-based formulation, is if your data G is perturbed by a little bit by noise, then your objective function easily pick up that amount of noise. Without knowing there's some noise in my data, we will easily do a reconstruction that overfits that amount of noise. And as a result, our reconstruction will have noise input. So these two challenges, it has been bothering these practitioners all the time since 1980s. There have been a lot of work. So we want to do something about it by changing an objective function. Before I propose which objective function we should go for, I want to talk about our motivation of going for this Wasserstein distance. So here we really want to reconstruct M, but we cannot see what is the true M, what is the wrong M, and what we can see is the data. So it is under the data fitting kind of name, but what we really want to do is model fitting. Therefore, in order to achieve do a very good job, we need to understand the underlying continuous dependence between the parameter M and the data F. So basically, you want to understand how the velocity change give you how the data change, that kind of relationship. Usually that's not possible for wave equation, but there are some exceptions. And one of the exceptions is 1D wave equation with constant coefficient. We also learned that in PDE course. There's one explicit solution to this particular 1D formulation, and that's the Lambert solution. So because it's constant coefficient, we can write it down the solution U based on the boundary condition. So we can see explicitly how a change of M can give me a change of U, which is also my wave data F in the 2D situation. So perturbation in M give me translation and dilations in the signal just by a simple observation. This tells me when I do not have the correct velocity, what I observe from the data side are most likely translation and dilation. Therefore, if I want to design an objective function that capture the essential changes, I want it to also capture this translation and dilation. But we need to keep in mind that translation and dilation are highly global changes. It's not local. And not surprisingly, L2 norm is not very good at capturing translation and dilation, which can be represented in this simple example. We have two wavelet type signals, the blue one and the red one. The difference between these two signals is simply a translation. And they can be very common in wave type applications because they can be generated by an incorrect velocity. One wave speed is faster, therefore your signal arrives earlier, and another wave speed is smaller, so your signal arrives later. So that's very common even you don't have the correct wave speed. And you compare them, there are differences in your data fitting approach by L2 norm. But in the end, it ends up to be a highly non-convex optimization landscape, which means if you will, using gradient descent based algorithm, you cannot converge to the global minimum unless you really in the global basin of attraction. You start with the global basin of attraction, which is quite narrow in this sense. And on the other hand, if we use the Wasserstein distance from optimal transport, measuring the same two signals here, it gives us a globally convex optimization landscape, which is what we really want, because we want our objective function to be able to capture translation and dilation. And that also brings me to the second part of my talk about optimal transport. So optimal transport is not a very new subject. It started with Monge in 1781, having the problem in mind. For Monge, Monge has two piles of sand, where you can think about there's a big pile of sand and there's a big hole. They have the same volume, and our job is to fill up the hole. But there are so many different ways I can do this filling up or this transportation. I can transport the left to the left, or the left to the right. There's so many out there. There are infinitely many choices. So Monge's problem was, which one gave me the minimum effort to move this pile of sand into this hole? It wasn't easy to solve because it is an optimization problem over a functional space. And also his original formulation is nonlinear in the transformation T that you choose. Therefore, there's not so much going on until 1940s. Kantorovich relax the problem a little bit. Instead of saying finding a map that map X to Y, Kantorovich say, why not we allow X to be mapped to both Y1 and Y2? So it's no longer a function, but it still can move some of the mass. Just move some from X to Y1 and move some from X to Y2. This simple relaxations immediately makes the optimization problem a linear problem. Therefore, one can solve it by linear programming. And he also pushed the application to economics, and that earned himself the Nobel Prize in economics in 1975. And later in the end of 20th century, there's a lot of mathematical analysts contribute to the theoretical side of optimal transport. So it's really a very solid foundation for applied math, which start to come up since 21st century. The first area was image processing, who adapted a lot of the methodology. And then recent 1 decade, we see a lot of application in machine learning, in inverse problem, and also recently in model reduction for hyperbolic PDEs. So I think personally, this list of application can be continued, and that's what we will be focusing on in the next decade. So this is an overview of the subject. And then for those of you who haven't heard about this optimal transport before, I want to use a cartoon to illustrate what is the cost function that optimal transport care about and why it is different from the LP norm. So again, you have two signals. They are not the same. So optimal transport first consider how can I make them the same. So we try to find a rearrangement map that makes them these two signals the same. So we put a little bit mass in the first bin to the second bin. After this single movement, they become exactly the same, and now it's my turn to calculate how much effort I made to make them exactly the same. And the effort is really the essence here from my perspective. It's the amount you move multiply the distance you move. And at each point, these two directions of cost are considered. So for LP-based norms, L1 or L2, we only consider the amount we move, only the vertical direction. But for optimal transport-based metrics, both directions, the distance and the amount, both are considered. And that's why earlier in that numerical example, you can see Wasserstein distance is globally convex in terms of translation, because at each point, such a horizontal change is considered. And also the mathematical definition is almost one-to-one correspondence with my heuristic definition. You have two probability distribution for F and G that have equal total mass. And you want to make F into G, and among all of the maps, particular map you want to, let's say for one of the map is T. So you are going to lift mass from, and how much mass we lift is F of X. F is a density function. So F of X denote how much mass you are lifting. And you are lifting this amount of mass from location X to location T of X. That tells you how you are going to transport. As a result, X minus T of X to the power of P denote your distance. If you choose P equal to 1, it means you care about Manhattan distance. But if you choose P equal to 2, it means you care about Euclidean distance. So here there's some freedom. but both the amount of mass I lift multiply the distance I move is the cost corresponding to location x. And once we integrate over the entire domain, that's the total transportation cost for this particular map T. And among all the possible maps that can do the rearrangement, I choose the T that give me the minimum cost, and that's our Wasserstein distance, and that T is also our optimal map. So that basically you can see this one-to-one correspondence to that cartoon. And there have been a lot of discussion in both W1 and W2, which means you choose Manhattan distance or quadratic Wasserstein distance. And in my research, we focus on P equal to 2 for most of the time. Okay, now we basically know the definition of the Wasserstein distance and how it's closely related to optimal transport problem. And I think for most of us, it's not surprising that Wasserstein distance can capture translation and dilation because it's all intrinsically in this T here, because T is allowed to be non-local, to be global, to be over the domain. But if you think about LP norm, the T is actually identity matrix, sorry, identity operator, because you are only allowed from this X to this X, and we only care about the pointwise differences. So that's what LP norm compared to the Wasserstein-based distance. So earlier we mentioned there are two challenges of the Sesame inversion problem that we want to tackle. One of them is local minima. We encounter a lot of local minima with L2 norm. And here we have a theorem to guarantee Wasserstein distance is much better than L2 norm in capturing translation and dilation. So the theorem is formulated as the following. Again, we have two probability distribution, one called F and one called G. And G is fixed, is my reference. And I'm going to define F as a translated and a dilated version of G. So since both F and G are functions defined on RD, I try to be more flexible to allow translation happening on every coordinate, and the dilation also can happen on every coordinate. So combining these 2D variables together, that's basically telling me how F is related to G in terms of translation and dilation. And that theta is uniquely the character of F. And the next, we compare the Wasserstein distance between F theta and G, which automatically will be a function of theta. And then we prove this function of theta is actually globally convex in terms of all the translation and dilation parameters, which is conveying the message Wasserstein matrix is globally convex in both translation and dilation. And earlier we mentioned why we care about translation and dilation, because that's exactly the direct consequence when you don't have correct velocity parameter, the wave speed coefficient in your wave equation. And this is a theorem, and we also have a numerical result to guarantee that's exactly what the property is reflected in the practice. So what you are seeing right now is a video that's showing the iterative change of the inversion. The left column is L2 based inversion, and the right column is W2 based inversion. So let me play it again. They start from exactly the same initial point, the same initial model. But as the iteration continues, these two different inverse scheme, they have different convergence paths. The L2 based inversion converts to something doesn't look like the Mamouzi model we showed earlier. And the W2 based inversion converts to the Mamouzi model. But more importantly, even if you don't know the underlying truth, which is the case in a realistic situation, you can just look at the residual. The residual is defined as the difference between the synthetic data and the real data. Since the objective function is basically a data fitting approach, the inverse problem is a data fitting approach. So whether your inverse problem is successful or non-successful solved, you can simply just look at how much data you fit. And the L2 based inversion has a lot of residual left there, while the W2 based inversion is almost entirely gone, which demonstrates W2 is a much better tool here to achieve data fitting. And because it captures the translation and dilation, so data fitting in this case also indicate the model fitting, and that's why we can convert to the true Mamouzi model. And that's about the first challenge. The second challenge is about sensitivity to noise, and that's also one big problem with L2 based inversion. And the theorem is the following. Again, we have F and G, two probability distribution. G is a reference, fixed. And now we define F as a noisy version of G. So F is imposed with additive noise, delta. Well, delta is mean zero with some variance, sigma square. Okay, now we have F and G, and if you compare the two signals under two norm, that's exactly the same as measuring the intensity of the noise. And that gives you the estimate of the variance of the noise. So your result will be asymptotically sigma square. That's something we already know from statistics. And what we realize is if you compare F and G under the Wasserstein distance, your estimate will be order of sigma square over n. So what I want to draw your attention is this n denominator. So again, the difference between F and G measuring the clean and the noisy data still depends on how much noise you have. But more importantly, it also depends on how dense your noise. And this estimate indicates that the denser your noise, the less the Wasserstein distance will be able to see it. So this is really counterintuitive. Usually the denser the noise, visually we can perceive the noise much better. Like let's say the picture I show in the bottom. The blue one is the big measure uniform density, and the red one you can consider to be F, the noisy one, and imposed with mean zero noise. So it's very dense noise, and it visually we think there's a huge difference between the blue and the red. However, under the Wasserstein distance, there's barely any difference between F and G, which means the Wasserstein distance between F and G here is 1 over n, order of 1 over n. And there are two reasons we can explain why we have such an interesting estimate. One reason is based on the definition of optimal transport and Wasserstein distance. It's always about the amount you move, multiply the distance we move. It's always that two aspects, and that's what I regard as the essence of this topic. So the amount we move in this situation is order of sigma square. It's about the order of variance. But as long as the noise is dense, you don't have to move much. You only need to move a little bit, because you move a little bit, immediately you can find some place to put this positive noise into this negative part noise. So the distance we move is 1 over n, and that's how we eventually have this n in the denominator. And that also can be reflected in our numerical example. So next, I'm going to do an inverse problem with a lot of noise. So the black signal is a one time domain signal from the wave equation solution. So that's supposed to be our true data. But now I'm going to pollute the true data, the clean data, by a lot of noise. And the noise is correlated a little bit with the true data. So what I want to demonstrate is it doesn't have to be IID noise. As long as it's mean zero noise, similar properties can be observed. Okay, so next in my numerical example, it's going to be the blue signal that our reference data. We try to match this noisy blue signal. And we can see the iterative convergence by this video. As iteration continues, the black time series on the right-hand side demonstrates the wave equation solution at a particular trace based on the wave speed on the left-hand side. So the black signal is iteratively changing, while the blue one is fixed because that's our reference data. So let me play it again. So the black is changing, but at the same time, our velocity wave speed reconstruction on the left is also converging. And it's not hard to see that it is converge to the Mamouzi model. And about 90 iteration, it matches all the convergence criteria, and the optimization whole system stops. So it's surprising at the beginning to see why this optimization stops, because by our visual eyes, the blue and the black are so different. By no way they are matching each other. And that's also the case if you measure these two by L2 norm. If you do the same inversion between the black and the blue signal under the L2 norm, you will reconstruct something really crazy, because L2 based inversion will try to match all those tiny noise. And that's because we were so used to pointwise comparison. Under the Wasserstein distance, the difference between the blue and the black is really minimum. Again, because it's always insensitive to high frequency noise. And how insensitive is H-1, which I will introduce next. So on the left, the reconstruction is a little bit noisy compared to the noise-free situation that we saw earlier, but there's no wrong features. For example, where there should be a discontinuity and the general trend of the wave speed is almost the same as the Truman-Misfit model. So for geologists, this figure still is very useful compared to the L2-based reconstruction. So earlier I said there are two ways to understand why Wasserstein distance is so insensitive to noise. One way heuristically to understand it is from the definition of optimal transport, because it's always measure how far away I need to move it. And another way to understand it is through its connection with H-1 norm. And that's also bring me to the third part of my talk, implicit regularization. The reason I call it implicit regularization is so far all the inversion you have seen, there's no regularization in it at all. I only have an objective function. So the fact that with purely an objective function, we can be robust to noise is an implicit regularization effect of that objective function. And this cannot just be, it's not only applied to W2, but also applied to a more general class of objective functions. This all starts with the connection from the theoretical community of optimal transport, studying the connection with H-1 norm. So Felix Otto and Cedric Villani in 2000 proved this asymptotic connection. If you compare two probability measures, mu and mu plus d pi being very small, then one can show the difference between these two is asymptotically weighted H-1 semi-norm, where the weighting means your sublift norm is not
Yunan, we cannot hear you somehow. Yunan, can you hear us? Yunan, still there?
positive norm, which is strong norm, S will be larger than 0, and this weighting function is going to be monotonely increasing, which means the higher the Kc, the bigger the Kc, the bigger the weight. Therefore, if you use H1 or H2 norm here, that means you have a lot of emphasis on the high frequency content of the residual than your lower frequency content. So you basically have an implicit bias in your data. And
sorry, it seems somehow your voice dropped out for a while. Maybe like which slides? Sorry about that. I guess maybe some technical issue of the WebEx.
Okay. So yeah,
Uh,
I'm sorry.
I'm not sure. Do you want to keep going or it's up to you?
Where did you get
Like this
yeah,
size, yeah.
this one?
After you talk about the Felix Auto and
Here one. Okay.
yeah.
Sorry. Yeah, maybe it was my internet
Sorry.
or something. No. It's yeah, definitely my fault. It's so yeah, Felix Auto talk about oops. Let me just turn this off. Okay. So Felix Auto proved this asymptotic connection between two probability distribution. And the recent work from Remy Prairie is about the non-asymptotic connection between two probability distribution. So in this sense, you no longer require the two probability measure you are comparing to be close to each other under some linearization regime. They can be further away from each other, as long as they can be bounded above and below by the same two constants. Okay, so what he showed was under such situation, W2 metric is exactly equivalent to H-1 norm. So both the asymptotic connection and the non-asymptotic asymptotic connection are telling the same message. Wasserstein distance, quadratic Wasserstein distance is related to H-1 norm, or in terms of spectral bias, it's the same power as H-1 norm. Okay, and now let's see the definition of H-1 norm. So here I also downgrade my inverse problem to a linear problem. In this sense, we will be able to see the solution exactly. So in this formulation, we define HS norm through Fourier transform. So you have a data which is AM minus G, and that's our residual between the left-hand side and the right-hand side. Usually we will do least square minimization, but here I generalize a little bit to HS space. So the definition of HS norm here is once you have the residual, you take a Fourier transform, but you don't treat different frequency content equally. This weighting c to the power of 2s is telling you how much you treat different frequency differently. If s is 0, then you will treat every frequency exactly the same due to Parseval identity, because that's L2 norm. But if s is positive, you have a lot of emphasis on the high frequency. And if you choose s being negative, you have a lot of emphasis on the lower frequency. So that's all due to different correspondence of this weighting term. So in our case, W2 is related to H-1. So basically, how H-1 related to noise is the same as how W2 will be robust to the noise. So we can see that by look at the solution at the frequency c level. So since this is a linear inverse problem, we were able to just compute every component explicitly. And the solution is at c level is a solution to the normal equation. And you can see here your data after taking a Fourier transform. If you have a positive S, your high frequency noise will be amplified because the Fourier transform of that noise is already very big. And your c to the power 2s is even bigger for higher frequency. So this data is amplified if you choose a positive norm, a positive S. On the other hand, if you choose a negative S, then even if you have a big amount of noise in the higher frequency content, it will be damped. And as a result, that frequency, that amount of noise will not be reflected back to your reconstruction because the high frequency noise content is damped by the negative choice of S. And this can also be seen by taking an inverse Fourier transform. Then you can see the solution in the physical domain. By choosing S being positive, this is a differential operator. So you are basically making your image more sharper. But if you choose S being negative, this is an integral operator, and the integral operator have the job of smoothing. So your reconstruction will be smoothed out and have less impact on the reconstruction. So that's the implicit regularization, not only for W2, but also for bigger class of objective functions. If you choose weaker norms, you have robust noise. But there's also other things that I think one need to be aware of, which is the negative side of choose of choosing a weaker norm. It's not that it's always good to choose a weak norm. And this theorem we prove basically showing the other side of the story. When you choose a weaker norm, the weaker norm will automatically treat higher frequency less seriously as it treats lower frequency because of this weighting here. And as a result, your data's high frequency is not taken into consideration. And therefore, your reconstruction resolution is not as good as a stronger norm. So this theorem, if we throw away the mathematics, conveys the message that when you use a stronger norm by choosing S to be positive, your epsilon, which is your error in the left-hand side, which we consider as resolution, is going to be small. But if you choose S being negative or even smaller than that, your epsilon is going to be big, which means you are going to make more error in the reconstruction, in the general L2 norm. So this is telling us what we lose by choosing a weaker norm. We lose the resolution. And in the end, we can compare this two sides of the property in this one single numerical example. So the example is very simple. It's just a linear deconvolution, kernel deconvolution. So the left column is L2 based result. The middle one is H-1 based result. And the right column is W2 based result. As we have seen so far, H-1 and W2 both corresponding to weaker norms. Okay, so the first row we see here is totally noise free, without any noise, like in the inverse crime situation. The L2 reconstruction is very accurate. It matches a lot of the edges and also the line, but the but the H-1 and the W2 reconstruction are not as accurate as the L2 one. So the H-1 still match the peak, still have basically the lowest number component exactly the same, like where it should be bigger, where it should be smaller, and the same with W2, but it failed to match the edges. Okay, so that's the situation of noise free. We lose the resolution by choosing weaker norms. Okay, next scenario is, let's think about our data has a little bit noise, 2% of noise. Then the L2 reconstruction immediately deviates from the noise-free situation. We have a lot of wrong features in the deconvolution, and that's a direct consequence that L2-based optimization framework, it overfits the noise so easily without any regularization. And H-1 and W2 based reconstruction in front of 10% of noise is still very similar to the noise-free situation, which is direct demonstration of the noise robustness. And the similar situation is also reflected in Bayesian inference, which I will just summarize a little bit. So for solving inverse problem, we can formulate it as a constraint optimization by doing objective function regularization, optimization algorithm, etc. But there's another approach is to consider this whole problem in Bayesian inference setting. And in Bayesian inference setting, there's also very important component. One is how to choose a prior information, prior distribution, and another is likelihood function. So in a separate work, we study what does it mean to use the Wasserstein distance as a likelihood function. And we realize that by using the Wasserstein distance as a likelihood function, you basically have an underlying noise model considering the noise between the synthetic and the real data to be multiplicative noise with a state-dependent covariance operator. This is very different from the usage of L2-based likelihood function, which means you consider a noise to be standard normal, additive standard normal distribution. And this is one difference, fundamental difference between different choice. But we also have one theorem to show that by using the W2 metric as your likelihood function, your reconstruction is more robust to perturbations in your data Y. And this is in the same vein as the deterministic illustration that we just showed 2 minutes earlier. So both deterministic-wise or Bayesian-wise, we can see the robustness of going for the weaker norms or Wasserstein distance, which is similar weakness compared to H-1. So finally, I think it's time for me to draw a conclusion. We were motivated by two challenges of the current Sesame inversion situation by using the L2 norm. One is trapped at the local minima, and the other is noise sensitivity. We propose Wasserstein distance from optimal transport theory. And the solution is Wasserstein distance has convexity in translation and dilation. That's exactly the continuous dependence from the perturbation your wave velocity parameter versus your wave solution. And that's the reason why we choose W2. So I also want to emphasize that my work doesn't indicate that we should use W2 all the time. I don't think that's the case. Maybe it doesn't worth it because computing the Wasserstein distance is not as cheap as L2 norm. But if your underlying problem give you such translation and dilation, such global continuous dependence, that's the continuous dependence local norms cannot capture. And that's the situation you should go for weaker norms. And W2 norm here has geometric property and can encounter such, can accommodate such transformations. And another difficulty was noise sensitivity. And earlier we explained the connection between W2 and H-1. And that's the fundamental reason why we would like to go for the weaker norm. And that's why in realistic inversion, we realize W2 is very robust to the high frequency noise. So that's the end of my presentation. I would like to take any questions.
Thanks, Yunan, for giving such a nice talk. Any question? I do have a few questions, if I may.
Sure.
My first question is, so it seems like you're working on 1D optimal transport, right?
Yes.
Each sensor is like you basically have the information in terms of time as a 1D signal. So when you do this inverse problem, you use a W2 as a fidelity term, basically. So how do you compute when you minimize that W2? How do you compute?
Yeah, that's a very good question. So this is actually one of the bottleneck. So the data we observe is the one that on the left-hand side we have seen already. It's a wave signal in both time domain and spatial domain. So in 2D, it's a function of x and t, and in 3D will be a function of x, y, and t. So it can be, so what we are facing in wave inversion is either 2D optimal transport or 3D optimal transport. So what there are so many different ways of doing optimal transport. I think I listed here. Okay, yeah. So these are the most popular ones I have seen a lot in different applications and also in the optimization community. So, and thanks to the rich development in the theoretical side of optimal transport, there are so many different formulations, and each particular analytical formulation, there are so many different numerical methods to achieve that. So therefore, in the end, there's a lot available for us to choose. So one is to solve the so-called Monge equation. You can compute W2. And you can also do 1D optimal transport, can do linear programming in the quadratic formulation, or using this Banmou-Brenier formulation, which is very, very nice, came up around 2000. Or recently, 2013, Marco Kantorovich say, if you add a little bit entropy regularization in your optimal transport minimization problem, you can use synchron algorithm to solve it very fast. And that's really make computer scientists very excited. And that's basically since 2013, the development of optimal transport really grow exponentially. And in the end, there's also kind of a trendy method to use sliced Wasserstein distance. It's especially useful in terms of very high dimension data, like 100 dimension. Then you can project the 100 dimension in S100. Then the projection result will be 1D. So you basically do a lot of 1D optimal transport. So all of them are available, and I've seen all of them in the Sesame community to do Sesame inversion. So what I have done personally